So I have 3 topics. I'll try to go quick. I really want to go through the second and third one in detail, so I'll go fast in the first one. But we're going to go, like I said, through 3 topics. I'm going to start right away with the first one that involves PRRS virus oral fluid ELISA. And these are all things that, cases that we have encountered during the last year in the diagnostic laboratory. So the oral fluids ELISA for PRRS virus, we've been running it for years now in the laboratory. But in the last year, about a year ago, there was a perceived increase in false positives for this particular test. A false positive in a negative population for PRRS, it creates a lot of headaches. You have to hold the animals, you have to retest, and so that's becoming more of a problem. So our first question was, is the test working properly? We checked with the manufacturer, we did a lot of repeats. It looked like it was working properly, at least the controls were. We tested a second lot, and it seemed to behave the same. So we started asking another question, is the test interpretation maximizing the guidelines, maximizing sensitivity and specificity, specifically the cutoff value that we use for this particular test? So I tried to use the data that we have at the lab already to try to answer that question. What would happen if we use a different cutoff value? So I needed to calculate sensitivity and specificity for different cutoff values. What I did is I collected data from the past 12 months, more than 4,000 results, and then I looked at what cases could I use to calculate specificity, so I needed negative hertz for that. I ended up selecting 2 systems for that, and to make it short, we ended up with over 2,000 results that we were going to analyze. 52 of them were positive, so that gives you the current cutoff specificity of 98%. For sensitivity, we need positive hertz. So again, we have less of that, but I did a search and I came up with 221 results that were known positive hertz, and 206 of those were positive, so we came up with a sensitivity of 93.2%. So that's what we get for sensitivity and specificity with the current cutoff, which is 0.4. And this is the distribution of the results. The blues are the negatives, and they are all down here, and this is these p-values. So most of the samples that are supposed to be negative, they are negative, very low SPs. Most of the samples that are supposed to be positive, they are actually out of the chart, more than 4. So it is a really good test in that sense, in separating positives and negatives. The problem we have is right there, and that's where the cutoff is. Should we move it a little bit farther down? That was the question. But in general, it is a good test that separates very well positives and negatives. So what we did is, what would happen with this data that we have now if we move our cutoff to 0.8 or our cutoff to 1? How does the specificity change? Specificity gets better, so we go from 98 to 99.6 to 99.7. So that's good. We started thinking, well, maybe we should do that. But of course, if you do that, you're going to hurt your sensitivity. So we want to know what happens with the sensitivity. And in that regard, what happened is we go from 93% to 88% to 87%. So we need to decide what to do about that. Are we willing to sacrifice that sensitivity to have a better specificity and not so many false positives? This is all assuming that we run 1 sample, right? But in most of the cases, we get more than 1 sample per case. And then what I did is I calculated hertz or case sensitivity and specificity. And that would be assuming that we call a case positive if there's 1 sample that is positive or more, and we call hertz negative when all of them are negative. And then I need to make some assumptions. I looked at the most common sample size for these cases, and I consider a case with 5 oral fluid samples. And I assume a prevalence of 50%, if really the disease was there, a prevalence of 50%, or actually a percentage of positives, because this is on a group, on a PEM base, not on an animal base. It wouldn't be prevalence, but 50%. So then when you calculate that, that's your case sensitivity and case specificity. You see that when you go from 0.4 to 1 for the cutoff, you go from 90 to 98 on specificity. So you're getting a lot better. And for sensitivity, you go from 96.6 to 94.9. So actually, it doesn't hurt your sensitivity that much when you move the cutoff. So that's basically all the background on why we decided to go ahead and change the cutoff to 1.0. And part of where this started too is at last AASB, Dr. Zimmerman briefly talked about a study in Canada by Tim Blackwell, and he was seeing something similar, and Dr. Zimmerman was seeing something similar. So when you put all together, it looks like it could be beneficial to increase the SP value. So that's what we recommended. So we recommended increasing the SP value. The SP values, even if you get a negative, those SP values below 1, depending on what you're doing, might still be informative. Some people are using them on vaccinated herds, and you might have information looking at the SP value, not just at positive or negative. So I would encourage you to keep looking at the value, not just the final result. But it certainly will help, I think, in negative populations. And finally, we do have a good number of samples that are individual samples for oral fluids. That is kind of like an exception, and those behave a little different. In those, you get even more false positives. And what we think it happens is that there's these animals that are off, and they throw the false positives. When they are in a group, sometimes that sample will get diluted, and you won't see it as a false positive. But when you do individuals, you're more likely to see it. So it may be necessary to even use a higher cutoff value for that particular case, but that would be the exception. So that's my story number 1. I think if you have any questions about this, we're going to try to have some time at the end. But like I said, I wanted to make sure I cover number 2 and number 3. Number 2 is about Senecavirus in processing fluids. And the way this one started was with a system that started reporting diarrhea and increased mortality in piglets during the first week of age. And that was happening at the same time in 6 different sow farms. The same system, the same flow had 5 other sow farms in the same flow that were not affected. But 6 sow farms, that was at the same time, that was very concerning. So they did a diarrhea workup. They sent me 5 to 7 pigs from each of the affected farms for a total of 32 pigs. Of course, there was a concern about PED, TGE, and what we found right away was that everything was negative, all the 32 pigs for PED, for TGE, for Delta Corona, and for rotavirus B. Now, there were some positives, occasional positives for rotavirus A and rotavirus C, but they had very high CTs, and there were a lot of the animals that were negative, so this didn't really help. There were some positives for E. coli, some for Clostridium, some for Clostridium difficile, but again, not all the pigs. And I didn't see lesions supporting that diagnosis either. So in histopath, some of the pigs had no lesions, some of them had mild villous atrophy. So I was a little bit lost right there. And then the veterinarian told me, why don't we test for Senecavirus? And I had been testing my diarrhea cases for Senecavirus for more than a year, never found a positive, and very recently I had decided to stop testing for Senecavirus. So I have to recognize that it was his suggestion, not mine. We said, okay, let's test for Senecavirus, see if that might be the case. And they were all positive for Senecavirus. All the 32 pigs positive for Senecavirus with an average CT of 23. It ranged from 18 to 34, but it averaged 23. So we thought we had a good story here, a probable diagnosis of Senecavirus. Of course, the lesions are still not very strong. You could still question if, any pig that you test maybe would have Senecavirus there. But it did, 32 out of 32 pigs with this type of CTs, it did suggest that it might have been the problem here. And then what happened with these farms is that all of these farms are sending every week, 3 processing fluid samples from all of these farms for PRRS virus monitoring. We had the samples at the lab, so we decided to go ahead and test those samples and see if processing fluids could be detected in if Senecavirus could be detected in processing fluids. It's a systemic virus, so I was expecting that probably we would find it, but I didn't know. And so what we did in these 6 farms is we tested the same, what I call week 0 would be the same week that I got the tissues with the piglets with diarrhea. That's the week where the diarrhea started. Remember, these tissues were sent right away because there was a concern that this might have been PED. So this is the week of the problem. And we found red and orange would be positive. We found 3 out of 3 or 1 out of 3 of the processing fluids positive in all these farms. But again, we don't know if maybe they are all positive. So we went back. We still had saved the processing fluids from the week before. So we went to what I call week -1, and we realized that only 3 out of those 6 farms were positive in processing fluids at week -1. And remember, there's no diarrhea here yet, no obvious diarrhea here yet. And then we went to week -2, and then all of these farms, all of the samples from all of these farms were negative. There was no diarrhea here either, no diarrhea here. The diarrhea was observed here. So I thought it was a good story, and it supported the role of Senecavirus as a cause of diarrhea in those herds. Remember, we have some other herds from the same system that are not showing diarrhea. So we looked at those. I only did 1 week. I really was interested in the same week that these are showing diarrhea. And I looked at all these other farms, and they were all negative. So that, again, supported the role of Senecavirus here as a cause of diarrhea in these baby pigs. So end of the story here. The clinical impact was low. Farms went back to normal. So it didn't seem to be a huge problem. But to me, it is important to consider Senecavirus. That kind of opened my eyes that we should probably consider it as a rule out during the first week of age. And then finally, if there is an interest, I don't know to what extent there might be an interest, but if there is an interest in monitoring Senecavirus, processing fluid may be a good sample. We didn't go farther than this. We don't know what happened in farms that might be endemic for Senecavirus, if it would be still a good sample for it. But at least in this particular case where there were some clinical signs, it looked like it could be a good sample for it. So that was my second story, and I'll jump to the third one. The third one is about PRRS virus and how we used, in this particular case, whole genome sequencing. In this case, what happened is that there were abortions in a PRRS stable sow farm. So it's not a PRRS negative farm, but it's stable. And whenever there's abortions, I get serum samples from sows that aborted. In this case, there were 10 serum samples, and they were all positive for PRRS virus. This is the serum from the sows. And with these CTs that you can see here, 3 of them are very high, but the other ones are pretty low. So we did ORF5 sequencing, and we got the sequence in 7 out of the 10. These 3, we couldn't get a sequence, but the other ones we could. And all of these Sanger sequences on ORF5 said that there was a 98% similarity to a vaccine, a PRRS vaccine. We're going to call it vaccine A. And actually, what happened really is we sequenced 1 initially. That's what we usually do. And we found that it was 98% similar to a vaccine. That didn't make a lot of sense, so we ended up sequencing everything else, and all of them were the same on the ORF5. So then what we did is, and that vaccine, what makes it even more weird is that vaccine had not been used for the last 2 years in that herd. So this was definitely unexpected. We wanted to know if that was, how close it was really to that vaccine. You see that there is a 2% difference, so it's not identical. And we wanted to know if that could be, how confident we could be that could be the cause of those abortions. So is it vaccine A, or is it a different virus? Is it a lateral introduction? We did whole genome sequencing in 1 viral isolate. We were able to isolate 1 of these. And so once we got the whole genome sequencing, we compare it to that vaccine and to other vaccines. And if you look at it gene by gene, this is what we found. Remember, ORF5, which was 98% similar to vaccine A. But if we start on ORF1, it doesn't really match anything very, very well, or ORF1B, it matches vaccine B, so a different vaccine. You keep going, vaccine B, vaccine B, vaccine B, and then ORF4, it matches even better vaccine A, and then vaccine A, vaccine A, vaccine A, and vaccine A. So looking at this, I thought, well, this might be actually a recombinant, and that has one part that's vaccine A and one part that's vaccine B. And so I got more help from our experts in analysis of whole genomes, and they did a recombination analysis for me, which is this is the right way to do it, the right way to look at it, not gene by gene. And what we found is that, yes, it was a recombinant. Yes, it was a recombinant between vaccine A and vaccine B, but it wasn't like I expected. One big chunk was vaccine A, one big chunk was vaccine B. What you can see here is this is the whole genome, started at nucleotide 1 and ending here at nucleotide 15,000 or so. And what you see is different stretches of the genome that match vaccine A or vaccine B. So that's the color coding. And this is the result of the fancy recombination analysis. But what I really like is, for me, to see it very simply, which stretches match one vaccine or the other. And you see that this is not a single recombination event. This is a strain that that is a result of several recombination events. And so it's been accumulating recombination between the two vaccines. And remember, vaccine A had been used in this herd, but it had been used 2 years ago. And vaccine B is a vaccine that was currently in use in this herd. So that's what we found. Our main question, was this vaccine A? The answer is no. By the way, we found it's also not vaccine B. It's a different strain. Did we create this strain by using two vaccines, or I don't know that. To me, some things that we learned here is, for these cases, that OR5 doesn't give you a good answer or an answer that makes sense. Whole genome sequencing can help. I also want to warn you that not in every time I'm showing you an example where we got decent answers from whole genome sequencing. It's not always the case, but we're learning more and more. And this type of recombination analysis, we can do them if we have whole genomes from your farms. So if we never do it until we have a huge problem, we're not going to have a lot of stuff to compare with. So I think it's good to try to do it, especially in cases where the OR5 it's not giving us an answer that makes sense. And finally, remember that multiple strains of PRRS coexist in swine populations, and they are probably recombinating more than we realize. And vaccine strains, I didn't want to put the vaccine names out there because I don't think it's one vaccine or the other. I think in general, vaccine strains circulate more than we realize. And so just keep that in mind when you're choosing which vaccines to use or switching vaccines. The other case that I know of where something similar happened was in a farm where they were intentionally rotating vaccines. And so after they saw something very similar to this, they started questioning whether that was a good idea to rotate vaccines that are live vaccines, even though they are supposed not to replicate too much outside of the pig. We all know that they do. And so we might get these recombinants that may or may not be more virulent than the vaccines themselves. So I think that's all I got. There were a lot of people that helped me with that, and as you saw, some of this work come from cases that were sent to the lab. So I'd like to acknowledge all those people that helped me with this.